In the previous lesson, we discussed finite limits as x approaches a finite value. The limit as x approaches c of f of x equals L. But what about infinity? How does that come into play? Let's first consider the definition of infinite limits. When does a limit equal infinity? Let f be a function that is defined at every real number in some open interval containing c, except possibly at c itself. The statement, the limit as x approaches c of f of x equals infinity, means that for each m greater than 0, there exists a delta greater than 0, such that f of x is greater than m whenever the absolute value of x minus c is less than delta. So here we have those deltas again, but now we have an m instead of epsilon. What does this all mean? Let's look at a graph to help understand. At our value c, we have a limit going to infinity. This means we have a vertical asymptote. So given some function f of x, and we note here our value c in the x-axis, then m is some boundary, some large value that we can get past. So if I claim the limit goes to infinity, that means I can get beyond any large number you name. So if we think about our challenge game again, if you say, can you get past 100? Now my job is to find a delta, a distance in the x direction around c, such that for any x within delta units of c, the corresponding y values, the f of x's, will be larger than m. So if you say, can you get past 100? Then I need to do a little calculation and find delta. So when I'm within delta units of c, then all of the y values will be larger than 100. Well, what happens if you raise the bar and you give me a higher value to surpass? If the limit is truly going to infinity, then no matter what m you give me, I can find a matching delta. Can you visualize what would happen as m gets bigger? What will happen to those bars representing the distance delta? They will get smaller and squeeze in closer to c. So as m goes to infinity, for no matter how big of an m you give me, I can find a matching delta if the limit truly is going to infinity. We can also talk about limits going to negative infinity. So the statement, the limit as x approaches c of f of x equals negative infinity, means that for each n less than 0, no matter how largely negative it is, there exists a delta greater than 0 such that f of x is less than n whenever the distance between x and c is less than delta. So now instead of an m, I'm using an n to represent a negative value. So no matter how low this bar is, how largely negative it is, we can find a matching delta so that all of the x's within delta units of c will produce f of x's, y values, that are lower than n, less than n. This means that the limit will be negative infinity. We also want to consider one-sided limits. Let's say we want to consider the limit from the left. Then instead of saying absolute value of x minus c is less than delta, we can say that x is between c minus delta and c. If we want to define a limit from the right, we can replace the absolute value of x minus c is less than delta with x is between c and c plus delta. This is easier to understand if we look at a number line. When we have x approaching c, just in general, remember that includes the limit from the left and the limit from the right. So our values for x could be on either side of c. So we say the absolute value of x minus c is less than delta because it doesn't matter if we're saying c minus x or x minus c, we're measuring that distance as a positive value. But if we're considering the limit as x approaches c from the right, now we only want x values on the right side of c. So x will always be larger than c. So when we're considering delta, we need x minus c to be less than delta, because that would be our positive value. If we consider the limit as x approaches c from the left, now the x values will be less than c. Since c is the larger value, we would have c minus x is less than delta. Note that if we have the absolute value of x minus c is less than delta, then we're saying that x minus c is less than delta and negative x minus c is less than delta, which is the same as c minus x is less than delta. If you get confused, try to draw a little number line to help you sort it out. How would we consider a limit of infinity numerically? Well, say for example we have f of x equals 3 over x minus 2, and we want to find delta so that f of x is greater than 100 whenever x is between 2 and 2 plus delta. Notice that this is a one-sided limit. We're only considering values of x on the right side of 2. So we want to figure out the delta that goes with an m of 100. So this chart here lists out different values of x near 2 and the corresponding f of x's. What would be our delta when m equals 100? Well, when f of x equals 100, then our x value is 2.03. So what's delta? Delta isn't 2.03. We're going to let delta equal 0.03 because it's the distance from 2. So if we consider our number line here, here's 2 and this is 2 plus delta, we want x values that are on the right side of 2. So if f of x is 100, the corresponding x is 2.03, then we need our delta to be that difference, the difference from 2. In this case, that's the 0.03. What if m equals 1,000? Then we would have delta equal 0.003. What if m equals 10,000? Then we would have delta equal 0.0003. Starting to see a pattern? So far what we have done is found specific deltas to go with specific values for m. But how would we prove the limit is going to infinity? We want to find a formula for delta based on m, like we did earlier when we found formulas for delta based on epsilon, so that we can say given any m, we can find the matching delta. So to do these types of proofs, we're going to set up the y information. In this case, f of x is greater than m. If we had a value for our limit of negative infinity, we would set up f of x is less than n. And simplify this to whatever type of limit we're dealing with, a two-sided limit, a limit from the left, or a limit from the right. For example, prove that the limit as x approaches 2 from the right of 3 over x minus 2 equals infinity. This is our example from above. So our setup here will be that f of x is greater than m. And our goal is to have x minus 2 less than delta. This is because if here's our 2, and this is 2 plus delta, our x's are on the right side. So x minus 2 is less than the distance delta. So substituting in, we have 3 over x minus 2 is greater than m. We need to make this inequality look like our goal inequality. So I already see the x minus 2, but it's in the denominator. So we can flip this. We get x minus 2 over 3, and then we also flip the right side to be 1 over m. We also have to flip the inequality. For example, if I had 3 is less than 4 and we do the reciprocal, 1/3 is greater than 1/4. So in this case, we now want to bring the 3 to the other side, and we have x minus 2 is less than 3 over m. So this matches the inequality we were looking for here, and we can say let delta equal 3 over m. Notice what we have here is an inverse relationship. In the problems we did in the previous lesson, we always had a direct relationship, like delta equals epsilon squared or delta equals epsilon over 4. A smaller epsilon would mean a smaller delta. But now what's happening is when we have a larger value for m, we get a smaller value for delta. And this makes sense because in our picture, as m gets bigger and bigger, then the distance down here, delta, would need to get smaller and smaller. So now we have a formula that given any m, we can find the corresponding delta that goes with it. So this will be our proof that the limit as x approaches 2 from the right of 3 over x minus 2 equals infinity. Here we have a new example. Prove the limit as x approaches negative 4 of negative 2 over the quantity x plus 4 squared equals negative infinity. I'd like you to pause the video and try this one on your own. I've already started the setup and the goal for you. Keep in mind that n is a negative number, and I'll go over it here in a moment. So filling in our setup here, f of x, which is negative 2 over the quantity x plus 4 squared, we want that to be less than n, since we're going to negative infinity. If we flip this over, we get x plus 4 squared over negative 2 is greater than 1 over n. Don't forget to make the reciprocal on the right-hand side. That's a common thing to forget. So now I want to bring this negative 2 to the other side by multiplying. But when we multiply by a negative number, that means we're going to flip the inequality again. So now we have the quantity x plus 4 squared is less than negative 2 over n. So we can take the square root of both sides, and that introduces the absolute value on the left, and then we have that less than the square root of negative 2 over n. This inequality matches the inequality we were trying to get. So we'll say let delta equal the square root of negative 2 over n. Did you get that answer? Did you feel comfortable with that answer? This looks a little strange, doesn't it? Because it looks like we're taking the square root of a negative number. But remember, n is negative. So really what we have here is a positive number that we're taking the square root of, and we have a positive distance. So now, given any negative number n, no matter how largely negative it is, we can find a matching delta, and that will prove for us that the limit of our function as we approach negative 4 is negative infinity. We can check this work by choosing some value of n, using the formula to find delta, and calculating the function at c plus or minus delta, and then make sure that the results are smaller, more negative than n. Or if we were checking something for going to positive infinity, we would check that the values were larger than m. In our example, let's say n equals negative 1,000. So then delta would equal the square root of negative 2 over negative 1,000. That works out to be approximately 0.044. So if we take our function f and we plug in negative 4, which is our c, plus 0.044, and we also plug in negative 4 minus 0.044, those y values will work out to be approximately negative 1,033. So that value is less than negative 1,000. So our f of x is less than n if we have our x value within delta units of c. What about horizontal asymptotes? These arise when we consider limits as x approaches infinity or negative infinity. So let's take a look at our definition. The definition of limits at infinity, if we let L be a real number, the statement, the limit as x approaches infinity of f of x equals L, means that for each epsilon greater than 0, there exists an m greater than 0, such that the absolute value of f of x minus L is less than epsilon whenever x is greater than m. Likewise, we can say the limit as x approaches negative infinity of f of x equals L means that for each epsilon greater than 0, there exists an n less than 0 such that the distance between f of x and L is less than epsilon whenever x is less than n. Okay, here we go again. Whole bunch of inequalities. Wait a minute. Epsilon is back. Where did delta go? Let's take a look at the graph. Once again, we have an epsilon challenge. If the limit as x approaches infinity of f of x equals L, then no matter what tiny restriction, epsilon, however small of an error you allow, I can find a large number m so that all of the x's larger than m will produce f of x's within epsilon units of L. This is similar to what we did with the limit of a sequence at the end of the previous notes. See, everything for x larger than m has to fit inside the given epsilon window around the limit L. So for every epsilon, no matter how small it is, we can find some value m such that for every x greater than m, the y values will be trapped within that error boundary. We will be within the allowed error. We will be within epsilon units of L. Notice that this m value is at the place where everything after it is within the allowed error. There are places where the graph crosses the error lines first, but we don't want those places because we need everything past m to work. So we pick the last place or somewhere just beyond the last place to indicate our value for m, so that every x larger than m will have an f of x closer than epsilon to L. Let's look at an example with some actual numbers. Here we have f of x equals 6x squared plus 5x minus 3 over 2x squared minus 1. And our task is to find m satisfying the definition for an epsilon of 0.1. Our limit as x approaches infinity of f of x equals 3. And we can just see that by looking at the coefficients of the polynomials because they both have the same degree. Our task is to find m such that f of m is within 0.1 units of 3. So here is a graph of the function, and we can just kind of see overall what it looks like. Notice the horizontal asymptote. We're going to be focusing on the part as x goes to positive infinity. So we can see the graph approaching 3 coming down from the top. So let's zoom in here where things start getting even closer to 3. I've indicated a couple of values. When x equals 25, then our y value is 3.10008. That looks pretty good. That's like 3.1. Would that be our value for m, 25? Well, f of 26 is 3.09623. Which one should we use? We want to use m equals 26 because the y value is within 0.1 units. If x equals 25, we're still too big. It is outside of the allowed error. There would be some value within 25 and 26 where we would exactly equal 3.1. But for these types of problems, we usually just find an integer value so that we can say everything beyond it is within the allowed error. We could say, yes, like m equals 1,000, and we'd certainly be safe. But the purpose is to try to find that m that corresponds roughly to where we actually enter those error boundaries. The algebra within a problem like this would be too complicated for our proof. So we'll use a simpler example for that. In this example, we have prove the limit as x approaches infinity of x cubed plus 1 over x cubed equals 1. So we'll set up the y information. We always start the setups with the y information. In this case, the absolute value of f of x minus L is less than epsilon. See, we're back to epsilon again because we're looking at a finite limit. Our goal is to make that inequality look like x is greater than m. So when we substitute in here, we will have x cubed plus 1 over x cubed minus our limit of 1, and that's less than epsilon. So there's a couple different ways we could simplify this. So I'll just do a common denominator. X cubed plus 1 minus x cubed over x cubed is less than epsilon. And so that becomes the absolute value of 1 over x cubed is less than epsilon, which we can do the reciprocal of x cubed is greater than 1 over epsilon. And I'm going to go ahead and drop the absolute value now because x is positive since x is approaching infinity. So then we have x is greater than the cube root of 1 over epsilon. So our inequality matches our goal, and we can let m equal the cube root of 1 over epsilon. Notice that as epsilon gets smaller and smaller, m gets bigger and bigger. Again, we have an inverse relationship with our variables. So for smaller error boundaries, we have to choose larger and larger m's, since we're doing the limit as x goes to infinity. We can check our work by choosing some epsilon and then use our formula to find m and calculate the appropriate y values. For example, let's say epsilon equals 0.01. M, which is the cube root of 1 over epsilon, would work out to be approximately 4.64. So we'll say let m equal 5. So if we calculate f of m, f of 5, we get 1.008. So not only is it close to 1, it's within 0.01 units of 1. It's within epsilon units of L. So this is how we would show that the limit as x goes to infinity equals our value L, in this case 1. In the previous lesson, we talked about limits as x approaches c of f of x equals L. X is approaching a finite value and we have a finite limit. At the beginning of this lesson, we considered what happens when x approaches a finite value, yet we have an infinite limit. Then we discussed the limit as x approaches infinity, when we have a horizontal asymptote and we have a finite limit. So there's one more definition to complete our set. What if we have the limit as x approaches infinity of our function and that equals infinity? So we have infinite limits at infinity. Whoa, what kind of functions do that? A lot of them. We could have the function that's just simply x squared, or e to the x, or 3x plus 2. Any function that goes to infinity as x goes to infinity. So even though this might sound complicated, it's actually a simple situation, and one that's very common. So our definition of an infinite limit at infinity. Let f be a function defined on some interval from a to infinity. Then the limit as x approaches infinity of f of x equals infinity means that for every positive number m, there is a corresponding positive number n, such that f of x is greater than m whenever x is greater than n. We can have a similar definition when we're dealing with negative infinity. In fact, this actually breaks down into 4 separate cases. So when working on these exercises, you'll have to pay attention to what's positive, what's negative. And the choice of m and n can vary. It doesn't really matter what letters we use, so my notes may be slightly different than what you see in the book. What does this mean? Now there's no deltas, there's no epsilons, just a bunch of n's and m's. So take a look at the graph. This just means that f of x gets infinitely large as x gets infinitely large. So as a challenge, if we want to think of it as our game, if I claim that this function goes to infinity, I can surpass any m you give me by just naming a large enough n. And every x greater than n will give an f of x greater than m. So if you tell me I need to get past 100, then I can find a corresponding n so that every x larger than n will produce an f of x larger than m. And with negative infinities, we would just talk about things being smaller or more largely negative. As an example, let's prove that the limit as x goes to infinity of x squared plus 4 equals infinity. So our setup is in the y direction as always. Here we have f of x is greater than m. Our goal will be to reorganize the inequality so that we have x is greater than n, and we're looking for a relationship between m and n. Putting in the function, we would have x squared plus 4 is greater than m, and if we solve, we have x squared is greater than m minus 4, or x is greater than the square root of m minus 4. And we don't have to worry about the plus or minus because we're considering everything going to infinity. So matching up our inequality here, we would say let n equal the square root of m minus 4. So we now have a relationship between the two. Notice that this is a direct relationship rather than an inverse relationship. So if we're considering our graph, if our function is going to infinity, then given any m, we can find the corresponding n. As m gets bigger and bigger, then our value for n would also get bigger and bigger. We have a direct relationship. And we can check this. If we choose some m and use our formula to find n, we can calculate the y value f of n and compare it to the value we're trying to exceed. So here let's say m equals 1,000. Then n would equal the square root of 1,000 minus 4, which is approximately 31.56, so we'll let n equal 32. If n equals 32, then f of n is 1,028, which is a value greater than 1,000. And any x greater than 32 will give us an f of x greater than 1,000. Let's organize all that we've done here into a chart. If you look forward in your notes, you'll see these charts that organize the 4 different cases we've considered. So keep in mind that c is the value that x is approaching. It could be finite or infinite. L is our limit. It can be finite or infinite. I also have the graphs here that correspond to each of the 4 cases. So let's consider when x is approaching c, a finite value. That's when we are looking for delta. So in our finite case, which is where we started with in the previous lesson, we have the limit as x approaches c of f of x equals L. So our setup here is the absolute value of f of x minus L is less than epsilon, with a goal of the absolute value of x minus c is less than delta. So we're looking for delta in terms of epsilon. When we have an infinite limit with a vertical asymptote, x is still approaching a finite c. So we're still looking for delta. We have the same goal. But now the setup is f of x is greater than m. If our limit is finite, that's when we see epsilon. So our finite case has our setup for epsilon. When we have an infinite value that x is approaching and our limit is finite, that's our horizontal asymptote. So our setup still has epsilon. That's because we have a finite limit. It's finite in the y direction. So our setup is the same. The absolute value of f of x minus L is less than epsilon. But now our goal is to find m so that all x's greater than m will produce y values within the allowed error. So a finite limit is when we have epsilon. A finite value that x is approaching is when we have delta. If both of them are infinite, then we don't see delta or epsilon. We have our setup as f of x is greater than m with a goal that x is greater than n. As I mentioned earlier, these cases expand out. You could actually make this chart into 9 boxes if you included all of the negative infinity possibilities. But don't worry too much about that. Just keep track of when it's negative, when it's positive. Draw sketches like these diagrams here to help you organize your thinking and to understand what you're doing with each limit situation. I cannot stress enough how important the idea of a limit is. Last time we reviewed the definitions of continuity and of limits of sequences and sums of series. However, it is even more interesting to see the intimate role limits have in the fundamental theorem of calculus. If a function f is continuous on the closed interval from a to b, and capital F is an antiderivative of the function little f on the interval from a to b, then the definite integral from a to b of f of x dx equals the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. Now you might be wondering, what's the big deal about this? This is just how we do integrals. They're the opposite of derivatives. Yes, but what do each of these parts mean? Remember that the definite integral is defined as the integral from a to b of f of x dx equals the limit as n goes to infinity of the sum from I equals 1 to n of f of xi times delta xi. When we're doing a definite integral, remember that we're calculating the area under a curve. And we do that by breaking it up into rectangles, adding up those areas, and then taking the limit as the number of rectangles approaches infinity, or the size of the rectangles approaches 0. A definite integral is a limit. It's a limit that defines integration. Remember that the derivative of f is defined as f prime of x equals the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. When we're doing derivatives, remember we're calculating a slope. We're finding the slope at that point. So that's the rise over run. We can calculate the slope approximately looking at the change in y over the change in x. But to calculate the slope exactly, we do that with a limit. The limit as delta x approaches 0. A derivative is defined as a limit. It's the ratio of the change in f to the change in x. Capital F in the fundamental theorem of calculus represents an antiderivative. It's a function with the slope given by little f. The fundamental theorem of calculus links these two ideas together. It links the area problem with the slope problem. These are two different geometric ideas, yet each can be calculated using limits, and it's the fundamental theorem of calculus that connects them together and brings together the concepts of integration and differentiation. This is what makes calculus calculus, and it's all based on limits. Without limits, we wouldn't have derivatives. Without limits, we wouldn't have integrals. And we wouldn't have math and science as we know it today. For most students, calculus is just more algebra, formulas and algorithms to memorize and just get through. But it's so much more than that. If there's any one thing that you take away from the study of calculus, it should be that the geometric concepts of area and slope are inherently connected through the study of limits. All of the other rules and techniques that make up the coursework either support or stem from this core idea. If you comprehend and truly appreciate the significance of this connection, you will maintain a general understanding of the calculus more deeply than that which most students of the subject ever approach. All of this work is based on limits. Limits are the seed from which grows the rest of calculus theory.